There are 4 index laws we're going to explore in this video. The first one involves multiplying indices or multiplying powers. There are certain patterns that happen that mathematicians end up using so often that they've combined them and summarized them into laws. Let's look at the pattern by first examining an example. If I take 3 to the 4th and then multiply that by 3 squared. 3 to the 4th is a shortcut for multiplication, and so is 3 squared, and I'm multiplying them together. So this is actually all multiplication. If I put 3 to the 4th in expanded form, and 3 squared in expanded form, and then a multiplication sign in the middle, and you see we're multiplying everything together. This is going to be the same as taking 3 to the 6th. What exactly it's equal to, I'm not interested in at this point, but what I'm interested in is developing a law that helps me know what to do when I multiply powers of the same base. They have to have the same base, and then instead of having to do this bit by bit and figure everything out, I can actually just add the indices together. So this is going to be the same as x to the 6th. Very important that you realize the difference between multiplying bases of the same powers, of the same indices, and adding terms with the same base. Because this you can't get any simpler. This is simply x to the 4th plus x squared. Because when I'm adding and subtracting terms, I need to find like terms to add together. And x to the 4th is going to be a different number than x squared. So that doesn't get any simpler. But multiplying them, I can put exponents or indices together. So that's the first law. These two are examples. If we want to generalize the law, we have to use symbols for everything. So I'm going to say this is x to the m, and I'm multiplying it by x to the n. And then I can show that that is the same thing as taking x to m plus n. So to summarize, multiplying powers of the same base but different indices, I can simplify by taking that base and adding the indices together for the new index. The next law involves dividing powers. If there was a shortcut for multiplying, then it's likely that there is going to be a shortcut for dividing too. So let's again take a look at an example first. I can write it like this, or I can write it in the algebra way with a fraction. Okay, in both cases, I'm going to take 3 times 3 times 3 times 3 times 3 in expanded form and divide that by 3 times 3. These are all similar factors, and that means that one of these 3's will cancel with one of those, because 3 divided by 3 is 1, and this 3 will cancel with this 3 as well. So that's going to be equal to 3 to the 3rd. I can do the same thing with x's, or with any variables. X times x times x times x times x divided by x times x. So it doesn't matter what number there is, we will always end up here with x to the 3rd. And so what we're doing there is subtracting the indices. So I can take x to the m to generalize, divided by x to the n, and that's going to be equal to x to the m minus n. So that's the second law. And this is our first law. But there's more. The third law involves powers of powers. If I take something that is already a power, such as 3 squared, and take it to another power, let's say to the 3, let's see if we can find a law to summarize what happens there. 3 squared to the 3 means 3 squared times 3 squared times 3 squared. right? That's what this 3 means, is I multiply what's in the brackets by itself 3 times. Well, using our multiplication law, I can add those together. That's going to be 3 to the 2 plus 2 plus 2. That's going to be 3 to the 6th. If I look here, 2 times 3 is also 6. So whatever number I have out here, that's how many times I'm going to be taking this exponent. And so taking a power of a power means that you can multiply the indices. So if I have x squared to the 3rd, then I can simply write 2 times 3, that's x to the 6th. So the general law is x to the m taken to the nth power is equal to x to the m times n. Just write the variables next to each other because that means multiplication. That's our 3rd law. And the last law is that anything to the 0th power is equal to 1. Doesn't matter what x is. If x is 3 to the 0, that's equal to 1. If x were 30,542 to the 0th power, that's also equal to 1. And this is a definition, but we need this definition for the other exponent laws to make any sense. Because consider here as a proof for this law that if I take x to the n and divide that by x to the n, then using my law number 2 here, I should be able to subtract the exponents. So that should be equal to x to the n minus n. Well, that's going to be equal to x to the 0. Okay, if I look at x to the n divided by n in a different way, then I say I'm dividing something by itself. Well, whenever I divide a number by the exact same number, I should get 1. So if x to the n divided by x to the n is equal to x to the 0, and x to the n divided by x to the n is equal to 1, then that should mean that x to the 0 is equal to 1. So anytime you see a number or a variable or a set of variables, even if I had something like 3x plus 2y minus 5, and that was all to the 0th power, that would always be equal to 1. Nice, easy thing. You have to remember it, but if you remember it, then it's easy to apply. Let's look at a couple of examples from the textbook work you'll be doing. And I'm going to take examples that are fairly similar to each other just to emphasize the differences between the laws and what can come up. So let's take this division law first. If I do 15m to the 4th divided by m, then my exponent laws or index laws work for variables with the same base. So I can also think of it like this. And I'm going to compare here the m to the 4th divided by the m. The 15, there's no other number, so it's just going to stay 15. But m to the 4th divided by m is the same as m to the 4 minus 1. Remember, there is a assumed 1 here because m by itself is just m one time. And so I can treat that when I'm dealing with the exponent laws as a 1. So this is going to be equal to 15 m to the 3. Yeah, the m and the two m's get joined together in that case. If I divide that same 15m to the 4th divided by 3, then my m to the 4th doesn't have anything to be divided by, so it's just going to stay at it as it is, and I divide the 15 divided by 3. So this is going to be equal to 5m to the 4th. Okay, so watch out for that, whether you're dividing by another variable or whether you're dividing by a number, how you work with it changes a little bit. Let's look at one where we're multiplying. And again, we'll take some different examples here. So 4a to the 3 times 2a squared. That means all the numbers are going to be multiplied together, and then all the variable terms will be multiplied together. So 4 times 2 is equal to 8. A to the 3 times a to the 2, that's going to be equal to a to the 3 plus 2. So that's equal to 8a to the 5th. Okay, if I expanded it all out and put it into expanded form, then maybe that's easier to see. And then multiplication doesn't matter what order you do it in. So I start by doing the 4 times 2. That gives me the 8. And then all the a's multiplied together, 1, 2, 3, 4, 5. I use the power to show that I'm multiplying 5 of them together. Okay, and this last example is a little bit simpler in that we only have a number and no variables. So we just multiply the numbers together and leave the variable term as multiplied by 1, just as it is. So that's the answer to that one. Okay, one last example with powers of powers. So here, if I'm going to take 2 squared to the 3rd power, I could first do the brackets and do 4 to the 3. And 4 to the 3, 4 times 4 is 16 times 4 is 64. Or I could also think of this as 2 to the 2 times 3, or 2 to the 6th. And that's also equal to 64. So either way, whether you first do the brackets and then the last exponent, or whether you first put the exponents together and then take it to the power of 2, in both cases you get the same answer. So if I have an x in there as well, and this time this x is only being squared, it's not squaring the 2 as well. The exponent only applies to the number right in front of it, whereas this 3 on the outside of the brackets applies to the 2 and to the x. So this is the same as taking 2x squared times 2x squared times 2x squared. And that means I have 2 times 2 times 2. That's going to be 8. And x squared times x squared times x squared. I'm multiplying variable terms with the same base, so I can add the indices. So 2 plus 2 plus 2 is 6. 8x to the 6th. And maybe you can see that right away by 2 to the 3rd being 8, and x squared to the 3rd, you multiply the exponents to get 8x to the 6th. Okay, that's the end of the video.